This video will introduce you to the combinatorics task of ordering and provide a formulaic approach for solving any ordering question on GMAT Quant. So let's take a look at our example questions from the introductory video. We could be asked how to line up 7 cars in seven parking spaces, or how many different orders 7 contestants could compete in a talent show. So since each of these questions involves the same number of elements and the same task of basic ordering, we would solve these questions using the exact same formula, the exact same approach. So the best way to think about combinatorics questions in general, whether they're ordering, permutations, or combinations, is by thinking of assigning elements to slots. So in this question, we'll define a variable of n for the full number of things being ordered. And in this case, it's 7. So we can picture 7 slots here. And we can think in terms of assigning elements to each of these slots in order. So if we're thinking about 1 car or 1 contestant, there are 7 options for the first slot. And then since 1 has already been assigned, there are 6 options for the second slot. And then since 2 have already been assigned, there are 5 options for the third slot, and so on and so forth. And this is why we will use factorials very often in combinatorics questions. Factorial means to take the number and multiply it by every integer on down to 1, inclusive of 1. And so to solve these questions, we would just need to evaluate 7 factorial, or multiply 7 times 6 times 5 times 4 times 3 times 2 times 1, getting us all the way to 5,040. Now that's a little bit more legwork than many combinatorics questions on GMAT Quant will require of you. Typically you don't have to multiply out such large factorials. There will be many ways of canceling factors as we look into the other kinds of combinatorics tasks. The next thing we need to know about ordering questions is that a complication might arise where some of the elements that you are ordering are identical in terms of a certain feature or indistinguishable for some ways. So what if we go back to the car scenario and we imagine that 1 car is black, 1 is yellow, 2 are white, and 3 are red, and we'll treat cars of the same color as identical elements or indistinguishable elements. Let's first think about each of these color categories as its own set of things to be ordered or arranged. So if we're thinking about the white cars independently, there would be 2 factorial, or just 2 ways to arrange them. If we think about the red cars independently, there would be 3 factorial, or 6 ways to arrange them. And so as we think about the full set of 7 cars, while all 7 of those cars are being arranged, there would be 2 such orders where the white cars are occupying the same slots, but could be switched back and forth with each other, and for our purposes, those are the same order. And the same is true of the 3 red cars. There are 6 ways in any given arrangement for those red cars to trade places with each other that we all treat as the same order. And so we will need to divide by those numbers in order to get back to the real number of arrangements that we are looking for. So the rule is that for every group of identical things, you need to divide by the factorial of that number and put that as the denominator of your fraction with the n factorial in the numerator. So in this case, we'll have 7 factorial over 2 factorial times 3 factorial. And I just realized I forgot to actually calculate that number, but that can be for you to do a little bit of mental math practice here at the end of this first video.